All right, let's talk about something absolutely fundamental to writing good concurrent Go code, the context package. Seriously, if you're working with Go routines, this is something you just have to know to build solid, efficient apps. So let's start with a problem I'm sure you've thought about. Picture this. You kick off some background work, maybe a heavy database query, but then the user gets impatient and just closes the browser tab. What do? How do you tell that Go routine in the background, hey, pack it up, nobody's waiting for your result anymore? And that, my friends, is exactly where context.context comes in. The absolute best way to think about it is as a little project manager for each and every one of your Go routines. It's the boss. It knows the deadline, it has the big red button to cancel the whole project, and it even carries around project notes. Okay, so let's get to know this project manager a little better. We're going to see what it actually does and why it is so critical for preventing your applications from just falling over. Because what happens if you don't have a project manager? Well, that background task we talked about, it just keeps on chugging along, burning CPU cycles, holding on to memory long after anyone cares about the result. We call these zombie tasks, and they are the silent killers of application performance. Context is the weapon we use to fight them. So every project manager comes with a standard toolkit. The big one, the most important one, is the done method. It gives you a channel. When that channel gets closed, it's the universal signal for pencils down, work is over. And if you want to know why it's over, the error method will tell you. Now, for the senior engineers in the room, here's a crucial insight. Contexts are immutable. You can't change one after it's created. This little detail is amazing because it completely prevents a whole class of nasty race conditions. It's beautiful. All right, now that we've met the manager, let's give them some actual controls. The power to set some hard deadlines and, a big red stop button. You're almost never going to use the base context directly. Instead, what you do is you create a new, more powerful context from an existing one. WithCancel basically gives you a function that acts as a manual stop button. Then you've got WithTimeout and WithDeadline, which are your automatic time-based kill switch. Now, it's really important to get the difference between a timeout and a deadline. It's simple but critical. A timeout is relative. It says, stop this job in 5 seconds from now. A deadline is absolute. It says, stop this job at 5 p.m. sharp. I don't care when you started. You can see why timeouts are just perfect for things like API service level agreements or SLAs. Let's see this in action because it makes way more sense with code. Here, we create a context that has a 2-second fuse. Then we start a task that we know takes 3 seconds. Our long task function is smart. It's listening to its context. So after 2 seconds, boom, the context's done channel closes, and our long task gets the signal and shuts itself down with a deadline exceeded error. Okay, pay very close attention here. This is probably the #1 mistake beginners make. You see that defer cancel function? You have to, must, always call the cancel function, even if you're using a timeout that fires on its own. Using defer is the standard, idiomatic Go way to guarantee it gets called. Why? Because it cleans up the resources tied to that context, like its internal timer, and prevents sneaky memory leaks. Don't forget it. Okay, so our project manager can stop work, but they can also carry around a briefcase. And in that briefcase are important notes specific to the project. Let's see how that works with Value With. Now, this is super important. With Value has a very specific, narrow purpose. It is not, I repeat, not a sneaky backdoor to pass optional parameters into your functions. You should only use it for data that is truly request scoped, stuff that needs to travel across your entire call stack, like a trace ID. So what are the right uses? The classic examples are things like a unique request ID, or maybe a user's authentication token. And for the senior devs out there, this is the magic that powers distributed tracing. You can stick a trace ID in the context at the very edge of your system, and it'll follow that request all the way through every microservice, letting tools like OpenTelemetry draw you a perfect map of its journey. And here's what it looks like in code. First, notice we're defining our own custom type for the key. That's a great little trick to prevent key collisions between different packages. Then in main, we attach the user Alice to the context. And look at the process function. It can pull that value right out of the context it was given, all without us having to change its function signature. It's super clean. All right, let's take all this theory and put our project manager to work in the environment where it is an absolute superstar, handling HTTP requests in a web server. And this is where the magic really happens. Go's standard HTTP server is brilliant. It automatically creates a brand new context for every single incoming request. If the user closes their browser tab or their connection drops, the server automatically cancels that context for you. That cancellation signal then flows down to all the work you started, your database queries, your other API calls, and tells them to stop. It's automatic cleanup. It's fantastic. Okay, to wrap things up, let's go over some pro-level tips and common traps. This is really the stuff that separates good concurrent code from great production-ready code. These are the golden rules, the commandments of context. First, by convention, context is always the first argument to a function, period. Second, never, ever store a context inside a struct. It just makes its lifecycle confusing and hard to track. And for the pros, it's not enough to just pass a context around. You have to use database drivers and libraries that are context-aware, so they can actually interrupt a network call when a context gets canceled. And on the flip side, here are the traps. We've already hammered this one, but forgetting defer cancel calling is the #1 cause of context-related resource leaks. It's a huge deal. Also, remember, once a context is canceled, it's canceled forever. You can't reuse it. And a little senior tip, contexts are cheap, but they're not free. If you're creating tons and tons of nested contexts in a super high-performance loop, it's something you might want to profile. Here is a great little pattern to make your debugging life so much easier. When your task stops because the context done channel closed, don't just return some generic error. Instead, check ctx.error to find out why it stopped. Was it canceled? Did it time out? Then wrap that original error using %w. This creates a beautiful, clear error chain that tells you the whole story. And finally, just to bring it all home, here's a quick cheat sheet. It ties all the main functions we discussed right back to our project manager analogy, a handy little reference for you. So you see, mastering context isn't just about learning some new functions. It's about gaining real control over your concurrent programs. It's about stopping waste, preventing leaks, and building systems that are truly resilient and efficient. The project manager is now yours to command.